Vsepr theory today. That stands for valence shell electron pair repulsion theory. We're learning about how to predict the three-dimensional shapes that can form and how to draw them. So valence bond theory was very complicated. So in 1957, Ronald Nyholm and Ron Gillespie created a simpler method called Vsepr theory to describe three-dimensional shapes. Now Vsepr again stands for valence electrons, or just valence shell electrons. That's the only one that we care about because they're involved in bonding and they repel each other. Okay, the key idea about this repulsion is that they want to get as far apart as possible in three-dimensional space. And you also have to remember that bonding electrons have lower energy than lone pairs. That means bonded electrons don't mind getting closer together, and lone pairs have higher energy, so they really want to get farther apart. In class, you're going to receive a handout entitled Valence Shell Electron Pair Repulsion Theory, and it's going to go through outlines exactly what I'm going to talk about in this video, but I'm going to go over it with you quickly. Now, there's a couple different major families of shapes, three-dimensional shapes, that you need to know, and these are them right there. There's 5 of them. The linear shape, the trigonal planar shape, the tetrahedral shape, trigonal bipyramid shape, and octahedral shape. Now you look, this group thing means it's got 2 groups around it. Trigonal planar has 3 groups, tetrahedral has 4, trigonal bipyramidal has 5, and octahedral has 6. Now the groups can either be lone pairs or they could actually be bonded atoms. Okay, so lone pairs or atoms. So if I have a lone pair and then 1 atom bonded, that means I'm going to be a linear shape. If I have 3 atoms bonded to me as a central atom, I have a trigonal planar shape. So when I'm talking about in respect to the central atom, so you really look at the central atom of each molecule, and based on how many things it has bonded to it, the central atom, that will tell you the three-dimensional shape. So the first family, this is the back of the handout you're going to be receiving. The first family that we're going to talk about is linear. And the linear family has 2 things bonded to it, okay? And there's really only one thing that can happen. So you have 2 atoms bonded to you. You are a linear shape. So here is our linear shape in 3 dimensions. You have a central atom and it has 2 things bonded to it. And those electrons, those are bonding electrons, are as far apart as possible. So in Vsepr, we assign 3 numbers. And the 3 numbers are as follows. So there are 3 numbers here. And the first number for Vsepr, it tells us what compound it is you have the total number of electrons. I've got 2 pairs of electrons. The second number tells you the number of bonding electrons. And the third number tells you the number of lone pair of electrons. So there's 2 bonding pairs of electrons here. The number is 220. Whenever you get a 220, you get this formation. Now an example of this would be the molecule BeCl2. Remember, beryllium breaks the octet. So the Lewis structure would look like this. And guess what? The three-dimensional drawing of it would look the same because it's just linear, and this is a piece of paper, or a board here. And so therefore we just show it as a linear shape. And that is the three-dimensional drawing of a linear shape. The next family that we're going to talk about is called the trigonal planar shape, and that's when you have 3 things bonded to it. For example, you can see you have BF3 here, and it fits on a plane, hence the name trigonal planar, so it would fit on a piece of paper. So the trigonal planar actually looks like this. The Vsepr numbers that you have would be, okay, so I have 3 bonding pairs here. So again, this is breaking the octet. So 3 total pairs of electrons, there's no lone pairs there, and all 3 are bonding, and 0 are lone pairs. So this is the trigonal planar. So whenever you have these Vsepr numbers, you can look at your sheet and you can see that it is a trigonal planar shape. So because it fits on a piece of paper, we can look at an example here. This is breaking the octet rule. This is BF3. You would draw the three-dimensional drawing exactly like you would the Lewis structure. So BF3 would just be, it looks like a Mercedes symbol, BF3 like so, and that's it. That's BF3. Trigonal planar shape. Fits on a plane, no problem, easy to draw, three-dimensional, looks exactly like the Lewis structure. So you can see there's also another one in the trigonal planar family. It's actually the numbers 3, 2, 1. So it has two atoms bonded right here and here, but it also has a lone pair. We're going to talk about that one in class, but this is the major. The 3 means it's going to be in the trigonal planar family. The 2 means that it's got two bonds here and here, and the 1 means it's got a lone pair of electrons. The next group is when you have 4 bonded atoms. This one right here, which is the tetrahedral shape. Now hopefully you see this animation well, but the angles between each one of these bonds is 109.5 degrees. Now this is actually a very, very important shape, and you're going to need to know that degree there. So the numbers we have for this, we can do a 3D drawing of this, but we're going to draw it as, an example would be CH4 or methane. Okay, so the Lewis structure for methane looks like this. The Vsepr numbers that we give this are, it has 4 total pairs of electrons, so we would give it a number of 4. And all 4 of those are in bonds, so we write a 4 there, and there's 0 lone pairs, so there we go. So those are the Vsepr numbers. So you could also have one where you have 4 bonds, or sorry, 4 pairs of electrons, where you have 3 bonds and 1 lone pair. And you also could have one where you have 4, 2, and 2, okay? So those are the major ones that we would look at, and each one would have its own unique shape. We're going to focus on methane though, which is 440. If I'm going to draw the three-dimensional drawing, I'm actually going to draw it down here so you can see it clearly. You start with your methane, and you want to draw it like it looks like a three-dimensional drawing. So what we're going to do is we're going to put an H here, an H here, an H here, an H here, and I'm going to try and draw it three-dimensionally for you. So what I want to do is I want to start with 2 lines, and these lines mean that they're on the board, okay? They're on my smartboard at this point. And then what we're going to do is we're going to draw one with like an arrow that looks like this. Now this funny looking arrow here, it means it's going out of the board, okay? So it's coming out of the board. And finally we have one more dash line, which means it's going into the board. And this is the three-dimensional drawing of methane. Now let's go back up and let's look at 431 and 422. You can see in the tetrahedral shape, when you have 431, you have something called the trigonal pyramid shape, which we'll talk about in class. And you can have 422, which is actually a bent shape. So we'll go over those to help you understand them further. But if you have 4 bonded electrons, 4 pairs of electrons, either bonded or lone pairs, you're in the tetrahedral shape. The angles that exist between you are 109.5 degrees. The next family is known as the trigonal pyramid shape. The trigonal bipyramidal shape is the next shape, which really looks like it has 2 triangle-based pyramids, one on top of each other. The numbers for this will be, there's 6 bonded. See, there's no lone pairs in our example above here. So the numbers that we would have for this are 6 bonded, or total pairs of electrons, 6 bonds, and 0 lone pairs on the central yellow atom. So I will show you how to draw the 3D shape of this. An example of this would be phosphorus pentafluoride would be an example. I'll show you the Lewis structure quickly here. So here is the Lewis structure right here. So this is the Lewis dot diagram, but is that a good three-dimensional representation of what's happening up here in our 3D diagram there? Well, to show the 3D drawing, I'm going to show it down here as well. What we need to do is we need to understand we have to draw that three-dimensionally. And to do that, we're going to start with just a normal phosphorus in the middle. Then we're going to have a fluorine going directly up, a fluorine going directly down, one fluorine off to the left, and so these solid lines are all on the page. Then what we're going to do is we're going to do a hashed line showing that this is going back, and a sort of an arrow going out. And if we look at this, if I'm going to draw some angles here, we'll explain the angles here as well. So the angles that we have between these fluorines here, this all fits on one plane. It's like a disc, or like on an equator almost. And you have 3 atoms there, and that's going to be 120 degrees between these. Now you also have, if I'm going to draw the triangles for you, so this is the triangle base here. And then I'm going to attempt to draw one of the triangles up to the fluorine. I know this is going to be confusing for some of you. The angles between this here is going to be 90 degrees going up from the equator to the fluorine and 90 degrees down. So if I complete the triangles here in 3 dimensions, you're going to see that there is 2 triangle-based pyramids. So we call it triangle bipyramidal shape. Okay. Now there's other shapes as well. Once we introduce lone pairs, our numbers start to change. So far, all of our examples have been all about total number of electrons, and all of them have been bonding, and none have been lone pairs. But there are other pairs as well once we introduce other types of shapes, once we introduce a lone pair of electrons. So instead of 5550 is the shape that you just saw right here, but you could also have 541 with one lone pair here. That's called a seesaw shape. Or you could have, again, 5 total pairs, 3 are bonds, and 2 are lone pairs. We'd call that a T-shaped. Or you could have 5 and 2 are bonds, and 3 are 3 lone pairs, and we call that a linear shape. If you had to draw them, you would draw them like this. Okay, so this is trigonal pyramid. This is the seahorse or seesaw. This is the T-shaped. And this is the linear, and you can see they're still doing the arrows. And instead of just putting an atom there, the X's are representing atoms. You're also showing the lone pairs and the bonds as well. I know this is confusing. We will talk about this more tomorrow. The last major family we're talking about is the octahedral shape. Okay, now the octahedral shape, if you take a look, it has that central atom there has how many atoms bonded to it? And the answer is 6. So the family will have 6, and in this case, it's always going to start with 6, this octahedral family. But to be an octahedral shape, you need 6 of them bonding, and you can't have any lone pairs, just like all the other examples that we've done that have not had lone pairs. And an example of this molecule that you're looking at there would be SF6. Okay, so sulfur hexafluoride. And if we draw the Lewis structure, it would look like this. So you can see that sulfur hexafluoride is breaking the octet rule. When we have to draw it three-dimensionally, we would draw it as the following. You start with a sulfur, and then what you do is you just finish with your fluorine going up and your fluorine going down. And then we have to have 4 atoms off the central atom. So that's an F right there. So we have to have 4 atoms off the central atoms of sulfur. And all those fluorines, they fit off a central plane. So I'm trying to show these ones here. I know that might be difficult to pick up on the video, but we want to show those. To show that they are on the same plane, what we do is we say 2 of those fluorines are coming out. Okay? And 2 of those fluorines are going into the board. So imagine this is like a spinning top, and I'm kind of drawing it on an angle. And the angles between these are as follows. So these are coming out of the board, and these are going into the board. And the angles, if I was going to draw dots between these atoms, they would all fit on a central sort of plane. And the angles between them, since there's 4 of them, and it's 360 all the way around, it's going to end up being 90 degrees. Okay? And the angles from this central post sticking up, going down, is also going to be 90 degrees between all the major plane, and the same thing on the bottom. You'll be able to understand this a little bit more, but this is how you draw the three-dimensional shapes. Just to give us a little practice before we go, what I'm going to ask you to do is draw some, I'm going to draw a loose structure, and I'd like you to tell me the Vsepr numbers for the following. Okay, what are the Vsepr numbers for water? Well, first what we have to do is we have to look at, go ahead, just take a moment, see if you can write it down. I'll pause the video here. Well, if you did it correctly, what you looked at is you saw that it has 4 pairs of electrons, 2 bonding pairs and 2 lone pairs. The total amount of pairs is 4. The number of bonding pairs is 2, the second number. And the third thing is that you look at the 2 lone pairs, so that's it. So these numbers will always add up to be this number. This is the tetrahedral family. So we're going to look at the tetrahedral family. In order to be a tetrahedral shape, it would have to be 440. This is not 440. It's 422. So let's look at the chart to figure out what it is. So the numbers that we have here are 442, 422. So it's this one here in the tetrahedral family, and it's bent. It's a bent shape, which looks like this. So to draw the three-dimensional structure, you can basically just draw it like the Lewis structure. So I'm going to draw it like a Lewis structure, but the addition is that I'm going to add a dash, okay, because this is actually the tetrahedral shape. So these lone pairs are coming out, and then you also have a lone pairs that's going in. Now, what are the angles between these? Well, if you remember tetrahedral, I said it was 109.5. But we also said at the beginning of the lesson that these lone pairs have very high energy, so they push each other, and these lone pairs have very low energy, so they end up sort of moving in a little bit. So they move towards each other a little bit. Oops, that looks ugly there. So these move in there, so the angles is less than 109.5. So when we freeze water and we measure the angles by shooting x-rays through it, through something called x-ray crystallography, the angles between ice crystals, or the actual molecule itself, it's based on this less than 109.5 degrees that are formed. Okay, this one's a little bit harder too. Let's predict the three-dimensional shape of this. It's CO2. Now you may be tempted, so go ahead and try and write down the Vsepr numbers. You may be tempted to write 4 here. It is not 4. We consider, when you do Vsepr theory, you have to consider double bonds as 1. So write that down as a note. So that means that's 2 bonded, or 2 pairs of electrons. Even though we know that's 4, we considered it to just be 2. So double bonds, you just count once. So you have 2 there, and on the carbon there is just 2 bonded pairs, even though we know that there's 4 there, and there's 0 lone pairs. That's the only trick there. And if you look at the shape again, it's a linear shape. So that's how you draw that structure. That's it for now. We'll talk about it more tomorrow.